The final section of this notebook happens to be the most important one. Let's talk about the area problems for polar curves. And the most important formula here is this one. Area inside a certain polar curve from the angle alpha to angle beta is given by 1/2 integral alpha to beta out of theta squared d theta. And the derivation kind of works as follows. For example, if you want to find out the area inside a certain polar curve from a certain angle, alpha to beta, in that case, what we need to do is set up some Riemann sum using sectors instead of rectangles, kind of like this. So we have Riemann sums decomposition, not by rectangles but by sectors, and then the sectors will approximate these green sectors by these red sectors. By the way, I think this program is randomized, so if I run it again, I'm gonna get different place. Yes, you can clearly see that the red sector is approximating the original green ones. Some part is missing, some part is going outside, and that is red area over here, delta A, can be calculated precisely by, well, area formula for a sector. 1/2 Ri squared times delta theta. Delta theta is the difference of angle theta, and of course, upon taking the limit, this delta theta will become infinitesimal d theta. Summing them all up, we're going to get a Riemann sum like this. Instead of sum of rectangles, we have sum of sectors. That's the only difference. And this 1/2 r squared will become the integrand 1/2 times r squared, and then this summation will become the integral alpha to beta, and this delta theta will become infinitesimal d theta, and we have a Riemann sum and Riemann integral. Okay, that was a quick derivation, graphical way to explain how things go, but after this discussion, we'll simply use this formula over and over again. Oh, by the way, if you have more than one polar curves, and then if you have a region captured in between, then you have to subtract one area from the other. We want to find out the outer curve and inner curve, and then subtract the area of the inside from the area of the outside. So we have big area minus small area. After simplification, of course, we get something like that. Here's an example. Example set, find the area of the region that lies inside the first curve and the outside the second curve. So inside this red cardioid, outside the circle, we're talking about the crescent region highlighted kind of like this. So which is R1 and which is R2 in this formula over here is pretty much straightforward. R1 is the circle, so this is going to be 1 squared, and R2 is going to be the cardioid, 1 minus sine of theta total quantity squared. What is not so clear is what is the starting and then ending angles, which are given by the crossing points. Look at this picture. Clearly, the red and blue curves are crossing each other at point 1, 0 and -1, 0 in rectangular coordinates. And are they really true? Yes, we can set them equal. R is 1 minus sine of theta, the red one, and also is equal to 1, the blue one. And then what do you get? We have a equation of sine function. This is really trivial. Sine of theta is equal to 0, so we have sine of theta is 0, so theta equals to 0 or pi. That's what I would like to do in typical situation. It'll turn out theta equals to pi to 2 pi. That's rather strange, but that's something you'll have to pay particular attention in polar coordinate problems. Let me emphasize again. In this formula here, what is R2 squared and what is R1 squared, that part is not difficult at all. Integral alpha to beta, that's the hard part. And even after setting up and solving the equation, it's not completely clear. Why not theta equals to 0 to 0 in pi? Because after all, theta equals to 0, then plug in theta equals to 0, then sine of theta is 0, so we have crossing point. But then again, if you move from 0 to pi, from polar angle, then the polar angle is moving counterclockwise. So angle 0 to angle 180 degrees, that kind of sweep will sweep through the first and second quadrant. I wish I had some animation. Alright, I paused and typed in some program. And here's the animation that's going to show you that the proper crossing angles are pi and 2 pi, not 0 and pi. So red dots and blue dots represent the moving particle models for the cardioid, the red curve, and the circle, the blue curve. And the gray arrow represents a polar angle. This animation begins from t equals to 0, stop, t equals to 0, and then as t increases to pi, we sweep through the first and second quadrant. First and second quadrant. So if you calculate the integral formula for that area computation from 0 to pi over 2, from 0 to pi, then we are going to end up with calculating the area captured by those two curves in first and second quadrant from here to there. That's not what we want. The shaded region is third and fourth quadrants down here. So we start from t equals to pi and then increase all the way to 2 pi. We want pi to 2 pi to sweep through the shaded region. Consequently, the integral has to be not from 0 to pi or 0 to 2 pi or anything, but it has to be pi to 2 pi. And then, well, okay, pi to 2 pi. Now the computation from this point on is pretty simple. R2 squared, 1/2 R2 squared, the cardioid part, 1/2 R1 squared, the circle part. Computation is just complete square breakup, and then some simplification yields 2 sine of theta plus sine squared here. And antiderivative of the sine function is going to be cosine. That's easy. Antiderivative of the sine squared comes from power reduction formula, 1 minus cosine of 2 theta over 2, generating 1/4 sine of 2 theta. After plugging everything in according to fundamental theorem of calculus, we get 8 plus pi over 4. And here is the justification by Mathematica. Oh, by the way, if you calculate the integral from 0 to pi, this is what you're going to get. I think you're going to get a negative number. Well, you got a negative number. 8 is bigger than pi, so we got a negative number. The reason is because we use from 0 to pi, the blue curve is outer curve. So if you want to find out the region between blue and red curve in upper half plane, first and second quadrant, then you'll have to switch R1 and R2. If we do not switch, then you get negative value. In any case, easy formula to work on over here, but it can be tricky over there. Let's see. Another problem, a little bit harder, but I'm gonna leave this to you. Let's move on to the third problem. I think this is gonna be a real challenge. Let me see. Is this really a real challenge? Actually, not really. So I'm gonna leave that to you as well. Okay, let's move on to this example. let me see which one is the one that I particularly like. Oh, it's this one. Okay. Now let's move on to problem A. Find the area of the region that lies inside of the both curves. So inside of sine of 2 theta, r equals sine of 2 theta, and also inside of r equals to sine of theta. If it is outside, inside, then we can use this formula over there. But inside of both, in that case we'll have to use this one, but which is R1, which is R2? Where? Well, the formula itself, the integral part is no big deal. Again, as usual, where is big deal. And there's no better way than to see a picture. And then here we go. Sine of 2 theta is sine of 2 theta is blue curve this time when t is moving from 0 to pi, and r equal to sine of t is the red curve, the circle. And the curve, and the region inside both curves, well, there are two of them, one in first quadrant and the other in the second quadrant. And of course, clever students will calculate only the one in first quadrant and simply double it. So let's calculate it up to here. Throw it up to here. No, I don't like the picture very much, so let's just go back to original. And then let's simply concentrate upon the right hand side. Now, how do we get my function? Well, this computation over here will be helpful. We have a crossing point, and then we can draw a line segment from the origin to the crossing point. When angle is less than that angle, that crossing angle, given as this black line segment, then we have to select a region inside the red curve. And vice versa, when the angle is bigger than the crossing angle and less than pi over 2, of course, because we are looking at only first quadrant, then we have to find out the region inside the blue curve. So we can decompose one with the other. Consequently, we are going to get two integrals. Let's see. And we have a second, something like that, but actually that's not too much of a big deal. By symmetry, we'll simply have to we'll simply have to calculate this first quadrant and the doublets, so you don't have to pay much attention to the second picture and this picture. So, where is the crossing point? This is a computation you'll have to do. So, sine of 2 theta is equal to sine of theta. And that's the computation you will have to do. And then you'll have to apply some trig identity. 2 sine of theta times cosine of theta is equal to sine of theta. So after simplification, what do you get? 2 cosine of theta is equal to 1. Great. Cosine of theta has to be 1/2. And what kind of angle do we get? Theta has to be pi over 3 or 2 pi over 3. We don't have to worry about 2 pi over 3. That's going to give you the angle in this second quadrant. We only concerned to theta equal to pi over 3, and then we're going to double that. As we see in this computation, we're going to double that part. From 0 to pi over 3, the inside of the red curve, sine squared, inside of r equal to sine of theta, so we have to calculate that integral. And again, this is because we have to double it. From pi over 3 to pi over 2, 1/2 times, well, we have to double sine of 2 theta. And we can use power reduction formulae, and then in the end, if you do it right, we're going to get this answer. And I didn't complete the problem. Again, looks like I can simply ask you to complete this one. We have all the pictures, all that is necessary, so please go ahead.